Hello dear and welcome back to my channel. If you haven't subscribed to this channel, please do subscribe. In this video we are going to be talking about how to use LP to model scheduling jobs for identical machines. We had talked about scheduling in earlier videos, so if you're interested in learning about it, you can just check earlier videos. Anyway, for today we want to talk about how to represent scheduling jobs using LP modeling. And when we talk about identical machines, we talk about machines that take the same amount of time for a particular job. For example, if the job takes 10 minutes to complete in machine A, it would take also 10 minutes to complete in machine B, C, D, E in every other machine. So it means all of these machines A, B, C, D, E are identical machines. So having said that, we are going to represent our jobs with, let's say, we have time TI. We have, let's talk about our jobs. We have jobs I, machine J. So this would be the notation. Let's talk about the load of a machine J. So the load of a machine J is the sum of the processing time of the jobs assigned to the machine J. So if we have jobs A, B, C assigned to machine J, some machine, let's call it J, and A takes 5 minutes, B takes 10 minutes, and C takes 2 minutes. So it means that the load of that machine J at this point would be the sum of this time, which is 17 minutes. So that's the load. Okay. So for this problem, our objective is to find an assignment that minimizes the maximum load over all machines. We want to minimize the maximum load. That means we don't want to have machines. Let's just illustrate. Let's say machine 1, it has this much load. Machine 2 has this much load. Machine 3 has this much load. We want to find an assignment that minimizes the maximum load over all machines. So we want to minimize the total time it takes to do all of the jobs assigned to this. Okay, now that we know the goal, let's start defining the other variables for this LP problem. So we have our variables as usual. This is where we start from. For our variables, we can say, let's represent it with xij. So this would mean job I, machine J, just like I said in the beginning. So we have xij, job I in machine J. This is what this means. So, and for xij, it will be represented with 1 or 0, where we have 1 if the job I is assigned to machine J. Is assigned to machine J. We have a 1, but if not, we have a 0. And I hope you see what I see. This is also a 0-1 LP problem. This, I see that it's a 0-1 LP problem. So this means that it's going to be hard, and we should start thinking about relaxation. So now that we've defined the variable, let's talk about the objective function. Now for the objective function, remember we want to minimize the maximum load. So it's min-max load in machine J. Min-max load J, where J goes from 1 to maybe M. Oh, we can put that here. J goes from 1 to M. We should put that on top of max. So this means that for load For load on machine J, we would have Xij, that's job I on machine J, times the time for it. That's the time for this job. Let's call it job 1. Job 1 on machine J plus job 2 on same machine J times the time it takes, plus that continues till we get to job N on machine J times the time it takes. So this is the definition of the load on machine J. I explained that simply a few minutes ago. So the time it takes for each job, the sum of the time it takes for all of the jobs on a particular machine, is the definition of the load. So now this means that our constraints, let's define our constraints. Our constraints, first of all, Xij, it's a constraint that it can only be 0 or 1 for all I and j. For all I, j. And the other constraint is that each job can only be assigned to one machine. You cannot break one job apart into many parts and assign them to different machines. In this case, your job has a constraint. One job has a constraint that it can only be assigned to one machine, and that is a constraint which we are going to express as X job I machine 1 plus X that same job machine 2 plus that same job machine 3 plus that same job whatever machine, right? Let's say M, because we have max M here, would be equals 1. That means it's going to be 1 at some point, right? And 0 at the others. So let's try to convert this to a linear form. Let's try to convert this to a linear, let's call it A, right? Let's try to convert A to a linear form. So to convert it to a linear form, we want to take an extra variable, and let's call that extra variable min t, minimum t. And what we are trying to express here is that max, let's use this. What we're trying to express here is that max from j equals 1 to m of load would be the same as min t, where each load is less than or equals t. So we're going to take the extra variable we have taken is a time that even the machine that has the most load cannot exceed. So it's more like placing a boundary for all loads on each machine. So let's say, for example, for some machine, let's say machine 1, we have load, the load on the machine 1 is always going to be less than or equals to. This is what this means. The load on machine 2 will always be less than or equals t. That way, the load on machine 3 will always be less than or equals to. So this means that if t is, let's say t is 110, just saying, it means that load 1, the load 1 can be 100, this can be 90, this can be 105, but it would never exceed 110. We are going to end this video here. In our next video, we are going to grab another scenario and try to use LP to model it. And I'll see you on the next one. And please, if you haven't subscribed, do remember to subscribe. It's totally free. See you on the next one.